Yes, thank you very much, Mark. I'm going to share my screen. Let me see if you can see the first slide.
Yes.
Okay, great. So today I'm going to talk about global modeling of seasonal mortality rates from river floods. It's a pleasure for me to start off this session. I'm Lorenzo Alfieri from CIMA Research Foundation, and I'm also a visiting scientist at the European Commission Joint Research Center, where I've also spent the past 6 years. And also that's where most of the work I'm going to present was performed. So I want to start by thanking my GRC and also non-GRC colleagues who contributed to this work. Okay, so let's start with the motivation. In spite of the recurrent seasonal patterns, every year river floods affects millions of people and kills thousands. Although, while a considerable body of research has attempted to characterize the seasonality of global flood hazard, with some relevant examples as early as 30 years ago, there is very little research to date which has focused on the seasonality of global flood risk. We know that flood victims are unevenly distributed, and most fatalities occur in the low and middle income countries due to exposure and vulnerability levels. So knowing the timing and the magnitude of floods is key to international humanitarian assistance and for management of resources. Okay, I'm going to start with a bit of introduction on the global flood awareness system, which actually contributed with some of its data for this work. So just a brief introduction, because GLOFASS has already been mentioned a few times in the past GFP virtual meetings. GLOFASS is an operational system for early detection of river floods in the future 30 days. So it simulates forecast of ensemble stream flow prediction for the next 30 days. And these are compared with reference flood thresholds, which are obtained from a long-term discharge reanalysis. And that's exactly what I'm going to use, this discharge reanalysis version 3 that covers the years 1980 to 2018 with daily simulations. Version 3 is not yet what you can see on the website. The current one that you see is version 2.1. So this will be hopefully online next year. A little bit more information on the GLOFASS reanalysis that I've used. It's GLOFASS reanalysis version 3 is the latest update with a new model calibration of a global hydrological model at 0.1 degree resolution globally. We use 1,226 stations for calibration. The main advances over the previous version is in the use of ERA 5 atmospheric reanalysis for the calibration, also for the use of a slightly different model configuration, which is the full list flood model, and also of an improved calibration strategy. So you can see now, for example, in the top left graph, that the Klein-Gupta efficiency has increased. These are cumulative distribution functions. So the more the curve stays on the bottom right, and the better it is. There was a substantial improvement. And also the bias, the relative bias has improved a lot, narrowing much more towards the 0%. So now more than 60% of stations are within plus minus 20% of relative bias. Okay, so talking more about this work, we first performed sort of validation of the flood timing simulated by the GLOFASS reanalysis. So for this, we compared model simulations with about 900 stations, discharge stations, where we had at least 10 years of daily available observations. In this validation, we found quite good results in the sense that the model could predict well the observed timing of flood peaks exceeding the 98th percentile, in this case, a threshold, which corresponds more or less to 1.8 years of return period. And the median difference was 22 days for for these stations, which is a conservative estimate in the sense that for the model results, we used all the 40 years of available um, model discharge, while for the simulations, we used only the available discharge. So this, of course, penalizes a bit stations with weak seasonality. Okay, so we calculated a number of seasonal output. So starting from the day of the day of peak, the mean day of discharge peak, sorry, including start, peak, end date, duration, frequency, and also, as you can see on the top right graph, the percent occurrence in different months of the year. So you can see how in different months there is a changing pattern of places which are more likely to experience discharge peaks. Also, the standard deviation in the top left is quite a useful indicator of flood seasonality. For example, you see with the brightest color places with a very strong seasonality. So where floods occur every year in the same days. And that is typically in the northern latitudes above 60 degrees, also on the rivers coming down from the Himalayas, and in West Africa. On the other hand, on the opposite, rivers which you see with darker colors are those with a weak seasonality, so where floods are less predictable, and that's where it's particularly important to have a flood forecasting system. Okay, so far I've spoken about flood hazard and particularly about flood intensity and frequency. Now I'm going to link this to flood risk. So first, flood magnitudes are linked to the corresponding inundation extent for different return periods. For this, we use the GRC flood inundation maps at the global scale by Francesco Dottori et al. And in this sense, it's not just a map-to-map matching, but it's really a grid-to-grid matching in the sense that each grid of the Glofas River network is linked to a so-called area of influence corresponding to the inundated area for different return periods. So inundated areas are then overlaid with population density maps from the global human settlement layer to estimate human exposure in all the world's countries, considering flood protection standards. So basically, expected annual exposed population is here calculated as the integral sum of the potential exposed population for frequencies between 0 and 1 divided by the flood protection levels, with the latter expressed in years of return period. Okay, I'm going to skip this one for time constraint, and we'll jump to this. We could estimate the annual population exposed to river floods, which in our estimates is 54 million people per year. You can see the spatial distribution of people exposed, which is mostly in countries in Southeast Asia, as well in some countries in Africa, typically Sudan and Nigeria. And then we move to link these estimates to estimates of flood mortality. So we used an approach proposed by Tanoa et al. In 2016, also used by Dottori et al. In 2018, where mortality rates per region and income classes, as defined by the World Bank, are inferred from two global disaster data sets, EMDAT and Munich Re, and so linked with flood exposure according to these links. So this is quite an interesting way, in the sense that although the mortality rates are based on estimate of flood exposure, which might be biased because they are model results, then the mortality rates are sort of calibrated with the use of these two global disaster data sets. So you can see the pattern of annual mortality, which is a bit similar to the exposure, and also the relative mortality, which is, in this case, is slightly different and highlights especially countries in general in Africa, in South America, and also in parts of Asia, while you see that in other continents, like in Europe or in North America, the mortality rate is quite lower. We estimated overall 6,000, 1,020 casualties from river floods globally each year. And now we move to the seasonal distribution. So we distributed this mortality according to the results from the global analysis. And we could estimate 73% of global annual mortality from river floods between July and September, and also 75% of the total occur in Asia only. So if you look at the top right graph, you see that global mortality from river floods is dominated by summer floods in Asia, which is this big red part, peaking in August, and then followed by mortality in Africa, which has a slightly delayed peak, which is in September. And you can see countries which are more the main contributor for flood mortality, which are Pakistan, China, India, and Bangladesh. On the opposite, the 6 months between November and April contribute to only 13% of global mortality. And this is due mostly to floods in South America and Asia. And the contribution of other continents is minor due to the lower exposure and vulnerability, despite some of them, like Europe and North America, have some peaks in their mortality rates, except right in this month. Okay, so let's go to some take-home messages, which is on average, river flooding affect 54 million people and kill 6,120 every year. And these estimates are in line with other figures reported in the literature. Summer floods in Asia are the main cause of mortality, with 63% of the total. Only 13% of global mortality is in the 6 months between November and April. And another important information is that 40% of the annual victims are just in 1 month as a country average. So of course, this is a different month depending on which country you're considering. So this is very important because we can use this information the best way and move sort of towards an annual planning of resources that should be made available for large-scale events, which need a lot of support. And for this, I want to conclude with one example. This is again related to the global flood awareness system, and particularly to a good forecast. This is about July of this year. On the basis of GLOFAS forecast, 10 days ahead of the seasonal flooding in Bangladesh, the UN released more than $5 million, making the fastest funding allocation in the UN history. So that consisted basically in distribution of cash and also with support emergency kits. And it's very interesting to see how this was done in a COVID era. So with face mask, social distancing, and proving really that pre-flood emergency support doesn't need to be done in a rush when the right information is available for use at the right time. So with this, I would like to conclude. I thank you very much. And I also want to leave you a few links, because most of the data set that were produced, all the output of this work is available for download in the GRC data catalog, as well as some other intermediate products. So thank you very much.